This is Mathematically Speaking, and I'm your host, Adam Allred. Welcome back to the show. Today we begin our journey into Mesopotamia. It'll be important to understand the history and the culture of each area that we visit on our journey through the history of mathematics before we can understand the mathematics that was developed there. We now begin our historical journey into Mesopotamia, or modern-day Iraq. One of the oldest civilizations to give birth to the West, the other oldest being Egypt. This one sits between the Tigris and Euphrates rivers, and this is where human civilization is able to flourish. In about 15,000 BC, we get the first evidence of wild grains being harvested, which means we have food. And now that we have food, we can do math. In about 7,000 BC, we see evidence of agriculture and livestock becoming more and more widespread. And in about 1800 BC, we get Hammurabi and his code. The Mesopotamian Empire lasts for about 10,000 years before Cyrus of Persia captures Babylon. And for that entire time, mathematics lived there, which makes sense as why we see so much mathematical influence from that area, such as our clocks being base 60 and the way we structure our calendar. Now, their style was cuneiform, meaning that they had clay stamps with different symbols to convey different ideas. It was not that there wasn't paper or that paper material to write on. It was just rare and it cost way too much to make. So however, clay was much more abundant in the area, making it the clear choice to begin writing. And this mathematical notation that we're about to go over may very well be the first explicitly mathematical writing. Remember, writing only began in about 4000 BC, and the idea of number has been around possibly as long as we have existed as humans. Probably before that, because primates can count. Which means it would make sense that as soon as we had written language, math would be the first thing to get written down. But this use of clay tablets made the mathematical notation very different from how we know it today, besides the fact that we use a different language entirely. They could not have stamps with 60 different numbers and then begin combining them after 60. Imagine how long that would take to do any kind of arithmetic. You couldn't begin a civilization, you couldn't have banking, you couldn't have trade if you had a collection of 60 stamps to work with, try to do some counting or some transaction. But their solution was ingenious. They stuck to one kind of stamp and used it in two different directions. A downward pointing arrow to denote 1, and a right-facing arrow to denote 10. But they also had positional notation. What do I mean by this? So if I listed off the digits 2, 4, 6, 8, 1 and asked you what number that was, you could tell me it was 24,681. That is because in our notation, we know which digits go in what places, and we have the tens place and the hundreds place and so on and so forth. And this makes any form of calculation very simple and very easy. If I wanted to add 10 to our number, I wouldn't have to add 1 10 times. I could just add a 1 in the tens place and know that I was actually adding a group of 10. In positional notation, math becomes much more a mental thing than a tactile, hands-on thing, which we will see in a further episode when we talk about the evolution of calculators. So remember again, they did all of this in base 60. So instead of a tens place and a hundreds place and a thousandths place, etc., it was a 60th place and a 60 squared place and a 60 cube place, and so on and so forth, increasing by groups of 60, like ours increased by groups of 10. I'm going to do my best to describe an example of their positional notation, and it might sound like old video game cheat codes. So if you're able to write this down, go for it if you want. So the number 740. In base 60, in Mesopotamian notation, it can be written as right, down, down, right, down. So right, down is 10, 1, 1, so 2. So that means 12 60 squareds, and then right, down, 10, 10, 1 is 21. So there are 21 leftovers and 12 groups of 60. What's almost as impressive is that they also had a decimal system, or rather a sexagesimal system, since it's in 60s. So a right-facing arrow could also mean 10 over 60. So another interpretation of our number, 740, could also be 741 over 3600. But there's no such thing as zero in this notation. There's no zero in mathematics at all until India invented the notation for it centuries later. Like, we'll switch to AD time frame when we get there. So in a situation like this, where a zero could have been placed to fill a gap where context is instead filling that gap, our number above could instead be interpreted, instead of 740, it could have been 44,460, and there would be a 0 after the 21. Now this positional notation this early in human civilization and this early in mathematics is extremely impressive. After this, when we get to Egypt, we transition to something called a marked value system, where a symbol has a given value and you play with those symbols to do the arithmetic. It's sort of like how we do money. We gather enough pennies so you can exchange all those pennies for $1 or quarters or whatever you have. Our notation is also like this. A vertical line is a 1. It symbolizes 1. But again, back to the representation of numbers versus the actual number. The actual number has inherent properties. So 5, for example, it's prime, it's 1 less than 6, it's the sum of 2 and 3, etc. But the symbol for 5 has none of those things. So in our schooling, we get so used to playing with symbols that we conflate the symbol with the actual number. But the Mesopotamian arithmetic would look so much closer than to our modern day arithmetic, with lining up numbers and finding sums. But instead of 10 being the biggest number in each place value, it's going to be 60. But back to the 0. Why wasn't there a 0? 0 is made a big deal out of by modern day mathematicians, and there's some debate over whether or not it's a counting number. Can you count with 0? There wasn't 0 for all that time until India, not because there was no concept of nothing. They understood you could have no things, but it could be that they just did not start counting at 0. Some mathematicians today consider 0 to be a counting number. You can count 0 things. If someone asks you how many grapes you have and you don't have any, you say, I have no grapes. We don't normally say I have 0 of them. Or there could be a difference between nothingness and 0. This semantic distinction is important in some arguments. When we get to India and discuss the invention of the number 0 as a numerical placeholder, their cosmology will help make sense of it, and perhaps the Mesopotamian cosmology could also help us.
And part of that Mesopotamian cosmology is the assumption that there was always something, particularly gods. Since there was always a god in existence, nothingness never actually was there. There was never just absence of any sort of being. Space and time was always filled with something. So there is a possibility that 0 doesn't exist in mathematical lexicon, because to the people and to the culture, there was never nothing. Even though you can't have particular things, I can have 0 grapes. But that doesn't mean that there was at once nothing at all, because numbers represented more than just an adjective for a group of things. Numbers existed. If 0, the number existed, that means at one point there had to be absolutely nothing.
Nothingness is often used to talk about the beginning of the universe, an absolute true absence of nothing. Absolutely nothing. But 0 is used to describe the absence of something specific, just like the number 5. It is used to communicate how many grapes you have. It still conveys information, a numerical account of how much of something you lack. So this is one idea of 0. This one puts it on a pedestal and lifts it to high esteem, but there's another perspective, that 0 isn't a big deal. It's a symbolic placeholder. Before there was a 0, numbers could only be understood via context, and much like the Mesopotamian system, with lots of confusion due to the lack of a place value system. 0 is a placeholder to make things less confusing. It makes calculating easier, and transitioning from a marked value system to a placeholding value system, that means the world. Because you're not carrying around an abacus, for example, or coins to represent everything to do transactions. You just have a paper and pen. Now that you have 0, there's no context needed. You don't have to hold the 0 in your head in an imaginary sort of way. But it could also be that their writing tech just didn't make sense for them to have a place-holding stamp. Remember, they only used 1. They just turned the direction of it and it's a new number. So these clay tablets have limited amounts of space, and so taking up space just to signify nothing is here, it could be considered waste. And I would imagine it would be very difficult to erase on these tablets if there was a mistake made. Now, the first mathematical feat that we will discuss is the Mesopotamian knowledge of Pythagorean triples. Pythagorean triples are numbers that satisfy the Pythagorean theorem. A squared plus b squared is c squared. But you might be thinking, wait, Adam, I thought Pythagoras was Greek. And you are right. Pythagoras is a Greek mathematician who we will dedicate a lot of time to when we get to Greece. However, there's more evidence to suggest that Pythagoras did not invent that theorem, rather he just formalized it. And we'll get to what formalization means also when we get to Greece. But Mesopotamians had a more arithmetical approach to this theorem, whereas the Greeks will have a geometric approach. They knew if you took any two numbers, doubled their product, subtracted their squares, and added their squares, you could get what is known as Pythagorean triple. numbers that satisfy the theorem. There's a clay tablet called Plimpton 322, named after the man who bought it for $10 in 1922 and then gave it to the Columbia University, George Arthur Plimpton, that contains 4 columns and 15 rows. The first row is just the number of each row. The other 3 all have numbers that satisfy the theorem. They're all Pythagorean triples, an example of one being 3, 4, 5. 3 squared plus 4 squared is 5 squared. 9 plus 16 equals 25. And it was estimated to be written about 1800 BC, which is when Abraham, in the Judeo-Christian tradition, would have led his people from Ur to Canaan, and this is also when the Code of Hammurabi was written. And the method that the Mesopotamians came to discovering this is unknown, but I can't imagine that it was any different than the way mathematicians invent new math today. Someone saw a pattern in the numbers, began playing around with these numbers and doing the arithmetic, and the only difference is that for Mesopotamians there was no need to rigorously prove the patterns that they saw. All that mattered is that it was correct. That's a very convenient thing about arithmetic. You don't need proof. If someone asks you for proof, gather a bunch of rocks, count them out, and you could do it. I could take 3, if I was looking at 3, 4, 5, the Pythagorean triple, and wanted to know if that was what satisfied it, I could square 3, I could make a square, a 3 by 3 square, and I would have 9 rocks. I could make a 4 by 4 square, and I would have 16 rocks. If I combined those together, I would have 25 rocks. But today, for any mathematics to be done, there must be a correct proof that is accepted by the mathematical community. And it's not that proof is subjective, but often the proofs that are being done today are so involved that they need to be peer-reviewed by all sorts of mathematicians and approached from different sub-subjects of math before it can be accepted as correct. We will discuss more of what proof means as time goes on and how mathematical knowledge varies slightly from general knowledge. But until we get to the beginning of the Greek mathematical empire, there is no concept of this. There is no concept of proof, and especially mathematical proof. The answer was the answer because it was right. Again, with arithmetic, you don't need to justify with words and theorems. If someone doubts you, you pull out a calculator or pull out some rocks. And on the next episode, we're going to finish the mathematics of Mesopotamia. This has been Mathematically Speaking. Thank you for listening.